For the next two lectures, we're going to be talking about two operations that are crucially important in computer science. And that involves searching data for a piece of information and organizing the data by sorting it so that we can efficiently find that information. And you probably use searching every day when you use either Google or Bing or some other search service in order to find some piece of information that you want. Now, we're not going to talk about anything as complicated as the algorithms that Google or Bing use to locate information today, but we are going to talk about some basic workhorse algorithms that computer scientists use daily in their programs to find information. So today we're going to talk about searching, and that's how to locate a desired piece of information. And then in the next lecture we'll talk about sorting, which is how to organize data so that search algorithms can efficiently find the information. Before we get into searching, we're just going to do a quick review of vectors because those are the data structures we'll be using for both searching and sorting our data. So that's the one data structure we've seen so far for organizing large groups of related data. So remember that a vector is simply a collection of similar information, such as a set of temperatures, and that we access the elements via indices. And the indices start with index 0 and go up to the size of the vector -1. And also, let's just quickly review vectors and arrays. We'll be able to search either a vector or array. We'll be using vectors to illustrate the data structures today, but arrays could be used just as easily. So remember that to declare a vector, you give it the keyword vector, and then in angled brackets the data type you wish it to store, then the name of the vector, and an optional size element, which usually we omit because usually we use vectors when we don't know in advance what the size of the vector is. In contrast, when we know how large our data is, we tend to use an array because it's more efficient, and in that case we specifically specify the number of elements. Vectors are resizable, so you can either explicitly resize them with the resize command, or you can add a single new element to the vector using the pushback command. Contrast arrays are not resizable. They're fixed size for all time. With element retrieval, when we're retrieving an existing element or when we're setting an existing element, we can use array-like notation using indices. Also, with vectors, we can assign a new element to the vector by using pushback to append a new element to the end of the vector. However, we can change existing elements using array-like notation. And with vectors, we can query their size because they're objects and they contain state information. But arrays are not objects, they do not contain state information, and therefore you cannot query their size. You have to keep their size in a separate variable in your program. Then finally we get to some advantages for arrays. You can initialize arrays with a list of values, whereas with vectors you can initialize them, but you can only initialize them to a single default value. So here I'm declaring grades to be of initial size 10, and each value will be initialized to 30. And even when I give an initial size to a vector, I can still resize it or add elements to it using pushback. Then finally, arrays are built-in objects and hence need no processor directive. But vectors are classes, they're objects, and we have to include them using the vector library. Okay, so that's enough for our review. And we're going to move now into searching. There's two search algorithms that we're going to talk about today. One is sequential search and one is binary search. And we're going to start with the simpler one, which is sequential search. So with sequential search, if we want to find an element, say we want to find Smiley in this array that you see in front of you, or vector, then we start at the beginning of the vector and sequentially search each element until we either find the piece of information we're looking for, or we reach the end of the vector, in which case we return -1 to indicate that we did not find our element. And we're going to assume that if we do find the element, we return the index location at which it's located. So you can see just by scanning this vector visually that Smiley is located at index location 5, so we'd want to return 5. Whereas if I was looking for Brad, I can see it's not in the vector, and I would need to return -1. And if there's duplicate names in the vector, let's say that Smiley was duplicated twice and it was at location 5 and 7, I would return the index location associated with the first instance of Smiley, which would be at location 5. So again, what we're doing is we're doing a sequential search. So when I look for Smiley, I actually start at location 0. And when I see it's not equal to Nancy, I then go to location 1. And when I see that it's not equal to Harry, I go to location 2. And I find, I go to location 2 and find it's not equal to William. So then I sequentially move to location 3, find it's not equal to Michelle, move to location 4, find it's not equal to Aaron, finally move to location 5, and bingo, it's equal to Smiley, so I return 5. So here's our function for implementing sequential search, and as you can see, it returns an int, which is the integer location of the, in this case, string that we're looking for, or -1 if we don't find it. And we're passing in two parameters, the vector of strings we're searching for and our target string. You'll notice that we pass the vector by reference because we don't want to copy its contents. That would be too expensive. We really don't want to modify it, so what we could do here is just say const to indicate that we plan to not modify the elements of the vector, but we still want it passed by reference so that we don't copy all of its state information. And then it's a simple for loop that allows us to step through our vector one element at a time. And basically, we just start at location 0, and then while n is less than the size of our vector, we increment, well, we don't increment n. While it's less than the size of the vector, we check to see if the target is at the current index location. And if it is, we return that index location. And then at the bottom of the for loop, we increment n so that we move to the next location in the vector. And finally, if we drop out of the loop without finding the target string, then we return -1 to indicate that we failed in our search. Okay, so that is sequential search. Very simple and also relatively inefficient. And the reason it's inefficient, as you can see, if we want to find an element that does not exist in our vector, we're going to have to search every element. And while it's not inefficient for this vector, you can imagine if, for example, we had a large database of names, say 1 million names, that it could be very inefficient to have to look through all 1 million names. And even if we find the name, you could probably intuitively imagine that on average we're going to have to search about half the entries in the vector. So even if a name exists on average, if we had a database of 1,000,000 names, we'd be looking at 500,000 names before we ever located the name we want. So that's going to be the motivation for our next search, which is called binary search. And to motivate it, think about a phone book and how you search a phone book for a name. If I asked you to find my last name, which is Vanderzanden, do you think that you would start searching from the first name in the phone book? I doubt you would. It would probably be very tedious to find my name. Instead, you'd probably open the phone book to close to the end of the phone book. And why is that? Well, it's because the phone book is alphabetized, and you know that V falls at the end of the alphabet. And furthermore, you're probably unlikely to open the phone book to my name on your first try. You might open it to the T's. So what would you do? You know that V falls beyond T in the alphabet, so you would go a little further in the phone book. And let's say you now opened it to the X's. Well, X's are beyond the V's, so you'd now go back a little bit. But at no point would you go to a part of the phone book that you'd eliminate it, because you'd know that my name could not be in the portion that you'd eliminated. For example, it could not be in the early part of the phone book. So this is the motivation behind binary search, which is if we have organized our data in a certain way, basically if we've sorted it, maybe alphabetically for strings or numerically for numbers, then we can take advantage of that order in order to find our piece of information that we're looking for. So the idea behind binary search is that you pick the middle vector element. And if you stop to think about it for a moment, that's what you should do if you have some uncertainty. If I say, let's play a game where I've chosen a number between 1 and 20, and I want you to guess that number. And I will tell you whether you've guessed too high or too low. You probably, if you're trying to minimize the number of guesses, are not going to start at 1, because you could end up having to do all 20 numbers. Instead, your best strategy would be to pick the middle number 10, and then let me tell you whether you're too high or too low, because you could now eliminate half the numbers and only search in the range that had not been eliminated. So for example, if you said 15, and my number was, if you said 10 and my number was 15, I would say you were too low, and so you would now eliminate all the numbers between 1 and 10. You would know that they were between 11 and 20. You'd probably actually next guess 15 because that's the middle of the range, and you'd be right. So that's the idea behind binary search. You pick the middle element in the vector, and assuming that it's sorted, you can eliminate half of the vector now. If by your good fortune the target element actually equals the middle element, you'd simply return the index of the middle element. But otherwise, if the target element is less than the middle element, then you'd repeat the search on the lower half of the vector. So for example, if I'm looking for Minnie in this vector down here, I'd first look at Mickey. It's the middle element. And you could argue, well, it could be Mickey or it could be Minnie. The way we do it is we simply add the starting index in the range we have not yet looked at. In this case, we haven't looked at any elements in the vector, so we start at 0. And we also add 0 and 7, which are the beginning and ends of the vector. 0 plus 7 is 7, and when we divide by 2 using integer arithmetic, we get 3. So that's how we compute the middle element, and that's Mickey. And Minnie, in fact, in this case, is greater than Mickey. So in this case, the target element is greater than the middle element, so we're going to repeat the search on the upper half of the array, or this half. Oops. Okay, so this half of the array. So here it is in action. We're looking for Minnie. So again, we add the smallest and largest indices, representing the smallest element we haven't looked at yet and the largest element. So that's 0 and 7. Perform integer arithmetic when we divide by 2, and that gives us 3. So Minnie is greater than Mickey. So down here I've blacked out the lower half of the vector because we know that Minnie cannot be in that half. We've sorted the vector alphabetically, so we know Minnie must be in the upper half of the vector. So now the vector that we need to search runs from 4 to 7, so we add 4 and 7, and actually you can see that it is a bit obscured here, so now it's not. You can see that 4 plus 7 is 11. Dividing that by 2 gives us 5, so our next entry to look at is Nancy. And you can see that Nancy is greater than Minnie, so our target element is less than the middle element, and therefore we're going to eliminate the upper half of the vector, which I've done here, and again we've obscured a bit of what we need to look at next. So now we only have Minnie left, so both the beginning and ending of our array is, or vector is 4. So 4 plus 4 is 8, divided by 2 is 4. We look at that element and bingo, it's Minnie, so we return 4. Okay, let's try a few more examples, and let's first try for Michelle. So again, we start with the low, which is 0, and the high index is 7. So 0 plus 7 is 7, divided by 2 gives us 3. So we're going to look at Mickey, and we can see that Michelle is less than Mickey, so we're going to eliminate the upper half of the vector, and we're now going to adjust the high to be 1 less than the middle element, because we don't even need to look at the middle element anymore. So we're just looking at the elements from 0 to 2. So 0 plus 2 is 2, divided by 2 is 1. So now we look at the item at location 1, and that's Harry. And we can see Michelle is greater than Harry. So we adjust our low to be 1 greater than the index location for Harry, and that puts low to be 2. So now we do 2 plus 2 is 4, divided by 2 is 2, and that's Michelle. So we would return 2. Now let's do an example for where the element we're searching for is not in the vector. Let's look for Nick. Okay, so let's again restart our search, and we start from the beginning. So low plus high is 7, divided by 2 is 3. So as always, we look at Mickey, and Nick is greater than Mickey, so we're going to be looking in the upper half of our vector. So we adjust low to be 4. It's 1 greater than our middle. And we're looking at elements 4 through 7 now. So 4 plus 7 is 11, divided by 2 is 5. So we're now going to look at Nancy. And Nick is also greater than Nancy, so it must be in the upper half of the remaining vector. So again, we adjust low to be 1 greater than the middle element, making it 6. So we're looking at the elements between 6 and 7. So 6 plus 7 is 13, and when we divide by 2, it gives us 6. And when we look, we find that Nick is less than Smiley, so it must be in the lower part of the vector. So we adjust high to be 5, which is 1 less than the middle element. And now you can see that we've actually eliminated the entire vector, right? Nick would have to fall between Nancy and Smiley, and it doesn't. And that's faithfully reported to us by our high and low values. The high value has actually moved below the low value, and that's how we know we can stop our search, is when the two values cross and low becomes greater than high. If that happens, we know that the element is not in the vector. So here's our search function for binary search. Again, we're passing in a vector and a target, and just to be consistent with the previous one, I'm passing in strings, but we could write one for ints or for doubles. We start and set our lower value to 0 and our upper value to the size of the vector -1. And again, that's because the biggest index is 1 less than the size of the vector. Now I do use a do while loop because I'm going to go through the loop body at least once. And I start by computing the middle as the lower plus upper divided by 2. I first check to see whether I found my target element, and if I have, I return middle as the index location at which it was found. Otherwise, I check to see if the target element is going to be in the upper half of the vector. So if the target element is greater than the middle element, I adjust lower to be 1 greater than middle. And otherwise, notice I don't bother to check to see whether the target element is less than the middle element. At this point, I know it must be because it wasn't equal and it wasn't greater than the middle element. Therefore, it must be less than the middle element. So I can immediately adjust upper to be 1 less than middle. And I repeat this while lower remains less than or equal to upper. Remember that if lower ever becomes greater than upper, we know we failed. And if we do fail, like with sequential search, we return -1. So our final thing is to simply test the program. We've sometimes talked about testing in this course, and I just want to quickly go over testing this binary search function. So we've declared a vector. We would initialize it with some names using pushback. Then we should check to make sure binary search works with each element in the vector, that it finds the name properly. So that's what this call is. It calls binary search with each name in the vector. Then we should check some extreme values that we know aren't in the vector. So we use aardvark, which is probably, unless we've really chosen a name that is, we'd probably not choose any name that had 2 A's to begin with it. We shouldn't, and we shouldn't choose any name greater than zebra if we're doing this test. So we'll check it with those 2 names. And I guess what I was wanting to say is we would make sure that when we initialized the names vector, we would make sure that all of our names were greater than aardvark and less than zebra. So we'd know that aardvark and zebra were extreme values that weren't in the vector, that fell off the left side and off the right side of the vector respectively. And finally, we test for a few non-existent names in the middle of the vector to make sure that it also returns -1 in those cases. So that concludes this lecture. In the next lecture, we're going to look at how we actually sort an array or vector in order to make sure that we can use binary search. Also, should just note that the number of searches for binary search is order log n. So if I had a slide for the number of searches for binary search, it would be, on average, we look at log base 2 of n. So let's need a subscript here. Log base 2 of n elements, where n is the number of elements in the vector. So log 2 is much less than the number of elements. For example, if it's 256 elements, log 2 of n is 8. Basically, you get the log 2 by dividing a number, seeing how many times you can divide 2 into a number. So 2, if you keep dividing 256 by 2, you could do it 8 times before you would reduce it to 1. And if you think about it, when we look at a 256 element vector, if we divide by 2, it's down to 128 elements. Then the next search is going to reduce it to 64 elements. The third one will reduce it to 32 elements. The fourth one to 16. The fifth one to 8, and so on. So each time we're having the number of elements in the vector, and log 2n describes the number of times we have to have it till we get down to a single element.